Hello everyone, this is Math with Ben. Today I would like to go over the limit definition of a derivative, an integral. And so let's start out with just a quick reminder of limits. Quick reminder for limits. So remember that a limit is an operator that takes some function, let's say f of x, and gives you kind of an estimate in a way. It will tell you what the value of that function approaches as some input x approaches a different value. So we'll write this as the limit lim of f of x equals L as x approaches a. So remember, as I just said, the limit, this operator tells you that f of x approaches some value L as x approaches a. So it takes two inputs, a function and a target spot on the x-axis, and it then whispers to you exactly what value the function is getting super close as it's hugging on the y-axis. So what are they important for? Limits are actually incredibly useful on their own for analyzing functions with gaps or hiccups, which are called like discontinuities, and a reminder that a continuous function is simply any graph that you can fully trace out without ever picking up your pencil off the paper. And they have a very special use in calculus. So you learn about them in calculus, and they're very useful for calculus. So in calculus, limits are used to take things to the absolute maximum or minimum. So the easiest way, something you might already know, that the easiest way to find the area under a curve is to pack it full of little vertical rectangles. To get the exact perfect area, you use something called an integral. So let's take a look at the limit definition of an integral. The limit definition of an integral. So an integral, just symbolized by this little long s, from some interval a to b of f of x dx is equal to the limit as n approaches infinity of a summation from I equals 1 to n of f of x sub I delta x. So this is the limit definition of an integral. And I know that it looks really scary, and you shouldn't let it freak you out, because what it's saying is actually very simple. I know it looks like a terrifying alien language, but it's just a formal way for mathematicians to write down an incredibly elegant idea. What this says on the left-hand side is that we are finding the total area under the curve of f of x from an interval AB on the x-axis with respect to x, as written by dx. That dx notation says that you're taking the integral with respect to the variable x, because sometimes you will have functions of multiple variables and you only want to take the integral of one variable. In a Calculus 1 course, you will only be taking the integral with respect to one variable, but it is very important to note down what that variable is. Otherwise, you have no idea what you're integrating over. Integrals can be very difficult sometimes. It takes a lot of calculus classes to really understand them and to get really good at them, but they aren't really that bad conceptually once you break down what this is saying on the right-hand side here. So to break down the right-hand side, let's start with this middle part, the summation. Let's start with the summation. So this is capital sigma It is a Greek letter. In mathematics, it represents a summation, which means you are adding little things together. Let's go over a little example to show you what I'm talking about. Oh, God. Let's do 5i equals 0, I. So here you're summing I from I equals 0 to 5, and what this is equal to is 0 plus 1 plus 2 plus 3 plus 4 plus 5, which is equal to 15. And that's all it is, really. When you have like the I component being summed over from I equals 0 to I equals 5, you plug in each value in between those. It'd be integers, of course. Each integer value in between 0 and 5, and you add them all together. So you're doing the same thing in our limit definition of an integral right here. So all it represents is summation, which is adding things together. In our calculus case, it represents adding up the individual areas of many separate rectangles under a curve. So then how do we find those individual areas? Well, the area of each individual rectangle is given by this, what was in the summation, f of x sub I, delta x. This is the area of each rectangle under the curve. So this expression forms a rectangle, and here's why. Let's look at the first term, f of x sub I. This is your usual function output where you take some value x and you get out some value y, or f of x in this case. It's normal function notation. The little I subscript just keeps track of which specific rectangle we are measuring in that exact moment. The term delta x, so this term right here, where delta is the capital delta, is another Greek letter, represents a physical, tangible width along the x-axis. So if we have a function here, whatever it is, and we're looking at like this rectangle, so this value here, I'll draw it in red, this value is f of x sub I. This value here is delta x. So remember, this is a height, and this is a width. So the area of a rectangle is width times height, which is equal to, in this case, again, f of x sub I, delta x. See, it's not that complicated. As you know, the area of a rectangle is just width times height. So I just showed you that the width times the height is the f of x sub I times the delta x. When we place this inside the summation, we are adding up n different rectangles, right? So we'll go back to this. We're adding up n different rectangles. That's what that represents. Starting with I equals 1, the first rectangle, of nth many rectangles with height f of xi and width delta x. Now the important thing to know is that every single one of these rectangles, they'll have a different height, right? The height here is different than the height here, and that's different than the height here. But each of these rectangles will always have a width delta x. The width will be uniform along all of the rectangles, no matter the height. So the height changes along the curve, but the width stays perfectly constant. Now when we add the limit as n approaches infinity, we are now adding up infinitely many rectangles. Now the question might naturally arise, or it might not. How on earth do you pack an infinitely many rectangles into a tight, finite little interval like AB? Remember, we're taking the integral on some interval AB of f of x dx. So we're packing, right, we have like this interval AB. and we want to find this area. How would we do that? How would we pack up infinitely many rectangles in a finite space? And it's a really smart question. The answer lies back in the left-hand side, or I just moved it to the right-hand side on this case, where you see a dx instead of a delta x. Calculus is essentially the beautiful study of infinity, right? There's other math classes that go into it and whatnot, and different types of infinity and whatnot. But just in calculus, just as there are infinitely big things, there are also infinitely small things called infinitesimals. To make this work, we look at what happens to the width of our rectangles as the total number of rectangles n approaches infinity. Remember, delta x is constant among each rectangle. So when you add more and more rectangles, to keep delta x uniform along each rectangle, you have to make it smaller and smaller and smaller. So when you have infinitely many rectangles, you're then making delta x infinitely small, which then it becomes dx, which is a tiny microscopic width, which is pretty much infinitely small. So the absolute magic of calculus is that adding up an infinite amount of these tiny areas gives us a perfect, finite, exact number for the total area, which is pretty awesome. So that is the limit definition of an integral. Now let's go over the limit definition of a derivative. So the reason I did integral first, normally in a calculus course, you will always go over the limit definition of a derivative first, but the reason that I went over the limit definition of an integral first is to get you familiar with the concept dx. And the reason that it's so important is because you kind of need to understand what dx actually is for the derivative. Remember, it's an infinitesimal change, right? Just like delta x is a change along the x-axis, dx is also in change along the x-axis. It's just infinitely many small. So let's start by going over notation. There is a couple notations for the derivative. There's like 5 or something, because it's a subject that was discovered by not one person, but many. So the 3 most used are Newton's notation, Leibniz notation, and Lagrange or function notation. So Newton's first, second, and third derivative look like this. So there'll be a function y, will have a dot above it. For the second derivative, it will have 2 dots above it. For the third derivative, it will have 3 dots above it. This is Newton's notation. The Leibniz notation, which is the most commonly used one, will have dy dx. So this is the derivative of a function y with respect to x. For its second derivative, it will have d2y dx squared. Now this is not actually an x squared, it's just representing the second derivative. And then it will have this d3y dx cubed. For the third derivative, this is Leibniz notation. And then function notation or Lagrange notation would be y prime, y double prime, y triple prime. This is function notation. We won't be using Newton's notation in any of my videos that I do because it sucks a lot. I don't like it. Because for higher order derivatives, like let's say you had a 5th order derivative, I'm not going to go draw 5 dots above an f of x because that's a waste of time. The main one I'm going to focus on is Leibniz notation, because Leibniz is cooler than Newton. But anyway, let's look at the first derivative dy dx. So how can I express dy dx algebraically? What could I describe this as some function in order for me to understand what it actually is? And that's a great question. And the answer lies in limits. So you're going to do the limit as h approaches 0. And this is the limit definition of a derivative. This is exactly what a derivative is, exactly what it means, and all that it's saying. Of f of x plus h minus f of x over h. And that's all. That's what a derivative is. That's the limit definition of derivative. So we can really also figure out what it means by looking at what a slope is. So what it represents is the slope, the instantaneous rate of change of a function, as you might have heard. And I'm sure you remember the slope, and you might not, of a line from algebra. So m, which is the slope of a line, is equal to y2 minus y1 over x2 minus x1, which equals delta y, which is change in y, over delta x. That may look very similar to this, right? dy dx. And it is very similar, and it represents kind of the same thing. dy dx, though, is infinitesimal change, right? While delta y and delta x was a physical, tangible change, dy dx really kind of isn't. It's infinitesimal. It's really, really, really small because it represents the change or the slope of a line in exactly 1 point. So it's actually no different, right? The dy dx is actually just the slope at a single point. The derivative of a function is the slope of a function at a certain point. And now I'm sure you understand the reason I spent so much time explaining dx, because dy dx isn't just notation, it literally is exactly what it means. So let's explain it using the definition with h. So this h right here. The top part, or the numerator, is the most confusing part of this. Besides, of course, h approaches 0 and there's an h on the denominator. Obviously, you can't divide by 0, so we'll get into that more. But let's explain the f of x plus h minus f of x. So what this is actually pretty cool. This is exactly y2 minus y1. Oops, y2 minus y1. Exactly what it is. That's all it is. This is equal to delta y, or in this case, dy. It is a change in y. Imagine that y2 is f of x plus h, and f of x is y1. All of a sudden, it becomes clear that the numerator isn't just a change in the y-axis. We have a new coordinate, f of x plus h, and an old one, f of x. And we are taking the difference between them to observe the change. And the reason that it is an instantaneous change is because f of x plus h minus f of x is a y value, f of x, and then a new y value, f of x plus h, where that h is approaching 0, right? Remember, the limit here, h approaches 0. So it's a really, really small change because it's f of x plus a infinitesimal change minus f of x. So it becomes really, really, really small. And the same thing happens with the denominator. So we start out with some x coordinate on the x-axis, and our new coordinate is x plus h. So delta x, right? Delta x is going to be x2 minus x1, where x2 is, in this case, x plus h, and then our x1 is just x minus x. So this just becomes h, which is delta x equals dx in this case. And as h goes to 0, again, delta x, just like delta y, becomes infinitely small, or in other words, dx. And thus we are left with a intuitive definition, right? dy dx, or the first derivative of y with respect to x, is equal to the limit as h approaches 0 of f of x plus h minus f of x over h. Oops. And that's it. That's all the limit definition of a derivative and integral is. Thank you for watching.